the live channel chat and you type them in there, like I'll try and keep an eye out for them. Otherwise, I promise I will take time for questions afterwards and I won't dip out on you. But first of all, I just want to thank everyone for coming and listening to this. It's definitely not like the most exciting talk to some people to do at like, the end of your workday or whatever. So I'm really stoked. And let's go ahead and get into it. So who am I? I feel like in a lot of talks, this is where people justify their ability to talk about this kind of thing. And so frankly, like I don't really have any formal education in reverse engineering. I don't have like a computer science degree. I don't have really anything that certifies, like I don't have any certifications in reverse engineering. So I hope that that's less of a disservice to folks who are listening to me, but I hope that it helps people like get into it and know that like this is something that I think is, fun and interesting to get into and to poke around at. And it doesn't have to be a job title, it doesn't have to be anything. But if you start doing it, it's a rare enough skill that frankly, like if you want it to be a job for you and you're interested in it, I don't think it'll be like a hard lift. But so I work in like the defense and aerospace industry, and I'm on like an incident response team, and that's in the context of where I do most re in the workplace. Where I got into it would have been in game hacking like 10 years ago, which isn't really like a scene I'm involved in anymore, but it was really good for getting into it. But let's go ahead then. So, what is reverse engineering? At a high level, we're just learning how something is working without really knowing, like, we didn't make it. So, in this case, it's like, hey, I have this exe, but I didn't write it. So, how do I learn about it other than just like running it and seeing what's easily observable? So that can be, in the context of a hypervisor or a debugger or whatever. But normally, if we're just like running a binary, we just kind of see what's presented to us, and maybe we see if Windows Defender or something starts screaming at us. So if we don't have the source code, then how do we learn about it? We can statically look at the binary itself and observe it, and we can also try to see the behavior of the process and see what it's doing in like a debugger. So what is the output, aka like why do we even do this? So malware analysis is probably why most people are here and interested. So we want to do that to see if it even is malicious sometimes. I've been asked to just see if we can get like a Yara rule out, like if we see something spreading or if we're getting intelligence that there's going to be some kind of malware campaign, something like that. If you like to write malware, it's a good way to learn how to write better malware. If you're into like exploit development, seeing how the binary works is probably always necessary. I'm not a career exploit dev, but every single time I've worked on something like that in my spare time, it's involved, going in reverse engineering at some level. Software cracking and hacking, DRM removal. That's sort of how I first started poking at things in hex editors, was going and seeing like, hey, I'm what 14 years old and I have no money, but I really want, StarCraft, or I really want whatever game. How can I see how I can force this to let me install it? And of course, like game hacking, seeing what you can observe and seeing how you can interact with it. So before really getting into it, there's a lot of initial concepts that we need to kind of speed run through. And some of these will probably be trivial for people who already know about them, and some of these will be maybe new to you. And either way, I think it's totally fine. It's just for the rest of the stuff to make sense, then we kind of have to talk about assembly and binaries and how they're created. Someone in a reverse engineering Discord that I'm in was kind of telling someone off, but they said something along the lines of, it's important to understand forward engineering before you understand reverse engineering. And I'm not saying that you should necessarily gatekeep that so much as that you'll probably have to try and pick up some of these concepts the more you get into it, because the easiest way to retcon what's going on is to understand how it kind of goes forward. So if we see here on the left, we've got like our source code, right? Really simple hello world. And if we write something like that, then we go ahead and we compile it. And compiling, I tend to kind of think of as two steps. And a lot of this stuff, by the way, will not be abstract, will not be exact. It's a little bit abstracted just so the concepts get across. So you'll see me like typing out some stuff, and please don't take that to be like exactly how a compiler behaves. But anyhow, so we'll have like compiled output code, which shows us this assembly. And so we can see each of these assembly instructions, which are really an abstraction away from opcodes, where the assembly gives us better of an idea of what's going on there. And a lot of this assembly, if you've never looked at it before, or potentially even if you've taken a class in it, may look like gibberish, and that's okay. We're going to get into what matters and kind of how to make it digestible in a minute. The other thing to keep in mind is that after things are compiled, with C at least, like you'll tend to have like a linker, and so you might have like external DLLs. You might have something along the lines of like functions that you didn't write. Like I always think of it as, printf is not a function that I specifically went and wrote, but it still somehow works. So the code is coming from somewhere, and it wasn't necessary to have it linked before getting that, compiled function in there. But I sort of think of that as an example of like a symbolic reference to something that doesn't exist within there that needs to be packaged in at some point. And then after we link things, we have like finally our .exe if we're talking about PE files. And so that lets us, have our thing that we can actually go and easily run, and we can run it on basically, any Windows system, so to speak. So once we get this .exe, though, we're seeing, oh, this is like hex code gibberish. How do we do anything with that? And that's an understandable question, and fortunately, I anticipated it. So, what is hex even? If you don't know what hex is, it's basically just a way of expressing values. So like we've got base 10, the way that we normally think of things. Like if we had the number 1,000 and we expressed it in base 10, the nice thing is that it's only 4 digits long. Because if we express that in a binary, it's however many digits long that is. I can't count beyond one hand. Then we'll also see in hex, like, oh, this is way shorter. So that makes it a little bit easier for us to read in some ways. And where that becomes helpful is because base 16 is, sort of a subset. This is probably a wrong way of saying it, but sort of a subset of base 2. It's easier to read as bytes. We're going to see this structure into things that are a multiple of 2 quite easily, and that's pretty helpful for going through. And we'll see why in a minute. So in this context, what it represents in the assembly instructions is a lot of the time opcodes. So like move the value 5 over to register EAX, being shown as B805, and then a section of O's, or zeros, pardon me, is sort of the same thing, but sort of not. I tend to think of opcodes as often being directly translatable to circuits on a processor. And you have things like microcode and whatnot, so that's not always the case, to my understanding. But something like B8 is probably literally a circuit that will move the value you have there in hex over to EAX, and that's like what the function it does. And if you move something into like a different register, it would have a different opcode as a result. So like move EAX, literally the opcode. Whereas if you move something somewhere else, it would actually be technically a different thing, even if it's still a move command. But we'll get more into that later. And then you also have data. You might have strings of text or other values. There's some headers, there's some meta information, and we're going to talk about that. So if you write a little bit of code, like we saw in our first image, you're going to have a boatload of outlet, right? But not all of your binary is code, and that's part of why it looks so huge. There's a significant amount of information that's literally just there so that the computer knows how to load it and run it. So like we have headers, like I mentioned, that have to be in there most of the time so that you can actually load this sucker. Like it'll tell the computer, or at least be parsed by the loader, is maybe a better way of saying it, what you need in order for this to run. And then you have different sections where different parts of your data go. We think of all data as code, or maybe all code is data. That might be backwards, but I'm not a philosopher. But generally, these different sections have different things that are identifiable. So if we type in like a static string, for instance, that's going to be referenced, it's going to be held in a different part of the binary than where your just straight up code is running. A way that it makes a little bit more sense to me is I think of it kind of as being like a book. If you get a book and you just start on page 1, then you might be slightly confused. You might have stuff that's not relevant to the story. Say it's like a novel or something like that. If you started at like page 1 of The Lord of the Rings, you would be wondering, if you had never seen a book before, like who the publishing house was and how it was relevant to Rivendell. It wouldn't make any sense. So that you don't generally start reading on the first page of paper. you have this predictable structure where we know that there's an entry point that we go to that we begin the story at. We know if it's a book like The Lord of the Rings, there's probably all sorts of stuff written in Elvish or something like that, that we have to go and find some kind of glossary to like understand what the hell they're saying. And then you might have indexes, references, footnotes, all sorts of stuff that essentially enables you as meta information to read the book. And I would think of the non code parts of binaries as being essentially that. So let's talk about a specific type of file. And this is not necessarily the easiest type of executable file to learn about, but I think it's the most common probably that you'll see obviously for malware. And like if you're like a PC gamer or something like that, you're of course a lot of the world is running on Windows, like it or not. And so PE files are very, very common. And there's multiple types of PE files. Like there's EXEs, kind of the classic ones. There's DLLs are PE files. Like if you look at them in a hex editor, they kind of start the same way. And so you'll see like each of those, for example, would have something called an MZ header, meaning like if you literally open it in a hex editor, we'll see that the first thing is MZ, which we'll do that in a minute. I'm going to try and make everything that we talk about in here have a practical example. And then you'll see like a PE header that's then parsed after that. And then you'll see like optional headers and maybe like a section table, that kind of thing. So all of that is there, partially because Windows is weird and has to have everything be backwards compatible. So like if you load a PE file by accident into like an MS-DOS machine, the MZ header is there so that your computer doesn't just like commit Sudoku. Then you have your sections, of course. I've put like a couple of them over here, and I think of those as sort of sub neighborhoods, if you will, of like the binary. So like in .text, we'll see like, oh, executable code is in memory locations hex 401,000 through hex 401,011. We'll see read-only data is in, 40200 through whatever. And so think of that as like some data, for instance, like a hard-coded string is just that you're using in like a print function. Like it's going to be read-only data because you can't change the hello and hello world. Like there's no reason for it to be there. So like it would to be writable or change. So it would be in read-only data. You'll have some stuff say something in an array that is inherently made to be manipulable, and that will therefore be in something like writable data or something where you can change things. And then you have stuff like resources and relocations, and we're really not going to go into that necessarily, but just know like everything that we talk about here, kind of the more that you poke at binaries, you'll be like, oh, well, I need to learn about this, and you'll just kind of gradually pick stuff up. So the notion that you're sort of diving into a really, really deep subject shouldn't scare you off from getting into things, because like there's definitely forward steps you can take to get forward movement, and to take what you know and pivot off of that, start asking and answering questions about things that you don't know. So let's talk a little bit about those headers that I made. So this isn't even the first header that you'll see, but it's kind of the first that I think are interesting. So when we go and we look at a hex editor in a minute, we will see the MZ header before these, but if we're basically taking a look at a hex dump of the PE headers in a PE file, we'll see that there's some interesting information that is useful to us. So, for instance, looking at the top one, the cough header, I've marked with the colors here where these are present in a hex dump, and we can literally go and see them anytime we go and check. So, for instance, we can tell this doesn't really have a pointer to a symbol table within the cough header. We can tell that it says it has no symbols. Symbols meaning like if you're not like a programming background, things like if you write like a function like exploit this to win or something like that, and you don't keep the debugging information because it's not technically necessary for the computer to run it with like a human friendly name, it might just get kind of wiped. But if you also just don't have anything like that, it's being and you'll have certain characteristics of like how something might be loaded. But let's go ahead and look more at the optional header here, because I think things start getting a bit more interesting. We can see in the second series of headers, there's the red 13E6 for the address of the entry point. That's where we see the code begin like execution typically. It may not necessarily be immediately where you want to be looking for what you want to see, but at the same time, it's where it's starting to run the program it's loaded. So .text then where we see it's loaded into the operating system, we would see that like the code itself begins at hex 1000, but at hex 13e6 is technically where the instructions start running, and maybe it references things above that. Maybe um, you'd have to go and literally go and check yourself and see what's going on. But then we could see, for instance, the base of the data. Like if we had a string like "Hello World," we could see that would potentially begin hex 2000. Then we can see that the image base that it's loaded into, because the structure of a binary is slightly different from when it's sitting in storage to when it's loaded into memory. Because, for example, in storage, you don't need, this sounds oxymoronic, but memory space to manipulate with your variables, right? Like you just need to know that you will need some space for variables when it's loaded. So your image base is where in memory you would start finding that. And section alignments, stuff like that is all stuff you can pick up. One thing that's interesting too is some of the headers are literally just like whatever size you make it, so to speak. Like they aren't necessarily always a fixed size. So you might see things like size of headers that are even used by the loader to tell you where to go. But I won't spend too much time on this, but just to say that if you need to learn some of the metastructure around your binary and what you're looking at, that's kind of where you go and check. So here I want to go and look at an actual binary because being talked at by a person is inherently boring. And we know a little bit. So we have this file that I got from begin2.re. It might be .begin.re, but I have the person's Twitter at the end. But I wanted to use binaries that people would know are safe and can actually go and like peek at themselves. But so let's take a look at the binary and, look at the different sections, talk about maybe what we think it's doing, and see if just from looking at it in a hex editor, if we could crack this by ourselves. So one thing that I like doing is this is called O10 hex editor, and it's absolutely not necessary for getting into reverse engineering. I think it's nice because it has these templates that you can apply and see, like, this is the MZ header I was talking about right here at the top. I'm realizing that people aren't seeing my mouse. So just know that the MS-DOS header, we can see at the top is highlighted blue, and we can see if we go and expand it, the properties down here that are available. So we can see like the used bytes, we can see
Hey, I'm sorry to interrupt.
paragraphs.
We
Yeah.
can't see your screen. We only see the PowerPoint.
Oh, no, thank you.
Yeah.
Let me fix that. All right. Hopefully you guys are with me now.
Yep, we can
Yep,
see
thank
it.
you.
Thanks.
Cool. Okay, yeah, apologies, but thank you for letting me know immediately. So I'll re-say a little bit of that, but we can see that highlighted in blue at the top is our DOS header, the MZ header. We can see each of these properties. If we click on specific ones, you can see that the highlight is changing and it's going through and showing what each of them is at. So we can tell the structure of this binary here, right? We can see if we go into the section headers, we have text, we have our read-only data, so we want to see maybe if there's any strings in here is kind of what comes to mind. I feel like strings are often, if you're looking at a binary, one of the first things that you'll look at. So we can see the pointer to the data, we can see where it starts, and then if we go even further down and we just go to read-only data, we can start to see everything in here. So we do see some strings. We see enter password, and then we see crack me, and we see either correct or wrong password. So not knowing anything in here, other than that, we maybe see some artifacts of actually, compiling it and everything. I think, and probably most of you think too, if we went and we literally ran this binary and we had to try and like solve the crack me, we could probably solve this just by looking in the strings. There's potential that the answer might be in writable data. and therefore kind of gibberish. And in that case, the first thing that would occur to me is like, hey, try to run it and try to observe the registers, but that's kind of neither here nor there. Now I'm going to go back to my PowerPoint, and hopefully you guys will follow me still. So let's talk a little bit about assembly now. So we mentioned this before, opcodes as CPU circuits, instructions are human readable. So the syntax that I tend to see things in is Intel. So you'll see, the instruction name, the destination of the data, and the source data. So I have it here as destination operand, source operand. So move EAX5 example moves the constant value 5 into the EAX register. And the destination operand is generally a register, right? Like there may be an exception. I don't think I know of any off the top of my head, but if you want to do an operation, you tend to have to save the operation somewhere so that you can use it somewhere else. And I sort of think of assembly at times as being a bit like those really, really simple toys where you have to stack rings across like 3 pegs or whatever to try and get the biggest rings on the bottom and the smallest rings on the top, that kind of thing. It's really like a lot of just shifting things into certain registers and shifting, pointers that point to memory locations, stuff like that. So we're talking about 32-bit assembly. And one thing that people can get tripped up on that we're really not going to focus on is something like EAX can technically be divided into smaller registers for if you want to control the flow of what you're doing. So something like AX, would literally just be 16 bits, but you'd be using it like EAX. Something like BX would be, again, 16 bits. And then you have pointers. The pointers are always 32 bits, like your ESI, EDI, ESP, and EBP. And we'll talk a bit more about what those are in a bit. But because they're pointing to 32-bit memory addresses, right? So they have to be 32 bits long. So I mentioned all those registers, and let's talk a little bit about what we'll often see them being used for out of like a straight up compiler. Like if you're just writing assembly, nothing is going to force you to use EAX as an accumulator, like, as I plus plus when you're going through your for loop or whatever. Nobody can force you to do it. It's kind of the cool thing about assembly is if you have like a violent hatred of dependencies and good practices, then you can just like run amok in assembly. So it may not work super well and stuff may break all the time and you may want to tear your hair out, but nothing's going to stop you. So EAX, think of that as an accumulator counter. I feel like it's holding your return values. EBX, I think a lot of times function parameters get passed there. Same thing with EAX. ECX, I may have misspoken earlier. You'll see counts for for loops in there quite often. And again, function parameters. EDX, I don't see used that often. I feel like when I'm looking at things, but you'll see it for generally used function names, that kind of thing. If you need to pass another parameter to it, you do it. Why not? You'll see index registers, right? So source index is often storing, constants or a pointer to a constant, that kind of thing. EDI destination index, often pointing to a destination for data or used as a destination for data. Then your pointers we'll get into in a minute. ESP and EBP are pretty important. They help us identify where we're at on the stack. And the way that the stack is used in the context of we're going to be talking about is by being able to recursively call functions. So if you've ever written, I don't know, I'll use Java as an example. That was the first language that I was kind of whipped into learning by, I don't know, maybe a angry community college professor or something. I don't know why they made us do that. But you would see that you start with your main method. And then your main method will call another method. And if it doesn't call another method, eventually your main method will end. So if you think about it, you're sort of recursively calling different methods or function that kind of build off of each other, starting from your first one. And the stack is the way that we recursively manage doing it. So then the other thing that we should talk about briefly are flags. And you won't really see flags per se unless you're looking at them in a debugger. Like, I don't feel like I see a lot of instructions that are literally just saying, do this to change this flag. It's more like the outcome of other assembly instructions. So comparing one register to another, for example, compare EAX, EDX. it changes a flag called the zero flag if they are not equal. And if they are equal, like you can subtract one and get nothing with it, then it'll be zero. So it's sort of like a Boolean remainder to some degree with that compare function. And then if we have JNE to some sort of location after that, jump not zero, it's saying, hey, if the zero flag is set to one, aka they aren't equal, they aren't zero, then let's jump over to that location. And if not, then it just continues running. So just keep a mind that there are going to be, especially if you're debugging weird things, there's going to be these weird flags that you'll see. Like I don't think I put this in this presentation, but one thing that you can see if you're looking at malware in particular is you'll see stuff checking to see if it's running in a debugger. And you may have to literally go and, if you're in a debugger, go and change the flag that is set to one if it detects a debugger yourself, and then allow the program to continue running. So having an awareness of those flags and kind of knowing like, hey, I see behavior that I don't really understand, maybe going and checking the flags and keeping an awareness of it if you're looking at things dynamically is really important. And now let's talk about the call stack. And this is something that's presented in I think, a really confusing way sometimes. It's I don't know, it's confusing, and you may not feel like you fully understand it following me talking about it. And if you don't, I would encourage you to go and like watch videos on it or read other people's explanations of how the call stack works, because I think that helps to pick up the function and how it all flows. So the stack, think of it like a deck of cards. If you put a card on top, then you're probably drawing from on top. You're not normally drawing from the bottom of a deck, compared to like a heap where it's first in, first out. Whatever's on the bottom gets pulled out first. So it's last in, first out data structure, and it's going to allow us to pass our variables and call a function and then return to where we were previously. And the way that that happens at a really high level is that we're passing pointers onto the stack so we can return to the function that we, called a function from. You will be doing things like pushing the variables on. Everything that you need is going to be on the stack. So in a sequence, how this works is you push variables onto the stack in reverse order. EBP is then pushed onto the stack next. That's our pointer to where we basically want our function to run. And that also, I believe, pops up a return address. And then EBP is then assigned the value of the stack pointer, which follows the top of the stack. So as things are added to the stack, in order to keep track of where they are and how far you've gone, the ESP pointer basically follows it. So the execution of that function is basically in memory taking place in between EBP and ESP. And EBP and ESP are sort of our boundary markers that we can return to where we came from and know how far we've gone. So then after EBP is popped from the stack, we return to that previous ESP value, which we pointed at EBP earlier, and then, or rather, which we held in EBP earlier, and then we can return to where we came from. So let's do this as an illustrated exercise, because that's way easier to understand than me just talking at you about call stacks. But in simple terms, we save where we came from with EBP, and we can use that saved ESP value that was saved to EBP to return us to the function that called us. So again, just so you guys know, if you're looking at my examples, they're meant to be very simple. This is not necessarily just like textbook compiler output, but don't be too worried, because reading assembly is way easier than writing. And as you see in these functions too, we're not going to be using a whole bunch of different assembly instructions. And if you look at assembly in binaries that you're interested in, I think you'll find that a lot of the instructions are kind of similar. Like you might really mostly be using like 10 different instructions most of the time. You're not having to memorize like 50 different functions or something like that. But so talking about what we had here, we have this source code where we want to basically pass integer A and integer B, and we want to subtract integer B from integer A. So that means that where we're going to look at is the beginning of this function call to the subtract function. So we've pushed our variables onto the stack here. So pushing, we see 05, we see 10, we see them right over there on the right. So the call stack, a lot of people will illustrate these as going up in memory. I tend to think of them as going down, weirdly enough, just because you're subtracting from the stack to add memory, stuff like that. So if you look at other people's tutorials for this kind of thing, don't be too worried if they're doing it slightly different from me. They may just be doing it backwards, but I think it's easier to be like, oh, push 05, and we see that in the same direction as we see, oh, push 10. And then we're calling subtract. So calling that pushes the return address onto the stack, and it jumps to the function address, which is assigned to subtract. So here we have our return address. We know it's right before EBP. So then after that, we set our EBP because the function is going to occur within this. And then we move the stack pointer to EBP because that's everything in there so far. And one thing of note, if you're just looking at like raw assembly, if you see push EBP, move EBP, ESP, a function is beginning every single time. Or maybe a better way of saying that is every single time you see a function begin, push EBP, move EBP, ESP is going to happen in 32-bit assembly here. So you would just see this called like RBP and RSP if you were looking at it in 64-bit. So here we have the scene set, so let's continue. So we have our local variables accounted for in the stack in this, and let's see how that's working. So where we were at before, we pushed EBP and we moved ESP to EBP, right? So if we push EDX onto there, so we have space for NA, and we push ECX on there so that we have space for, pardon me, this is integer A, and EDX was for integer B. Then we move EBP plus, the value into EDX, and then we move the value A into ECX because we know that they are from that distance relative to EBP. Then we can actually do our subtraction and store it in, and then we can, we can extend ESP so that we have room to store our value for NC when we actually do the maneuver. So now we're performing the function. Notice that we're not, like I mentioned, manually necessarily moving ESP around on our own every single time. If we're pushing and popping, we are actually moving ESP with that. It's like a function of push and pop. So again, like not everything that you see expressed in assembly, it's sometimes more than that. Like push EBP isn't just EBP. It's also pushing a stack pointer. Pushing EDX onto the stack also moves the stack pointer, that kind of thing. So then we can see here that where we left off before, we can now subtract EDX from ECX and store the value in ECX. And then if we wanted to, we could move that ECX value to the integer C location. And then we can, following that, save that to EAX so that we can return. So at this point, we've performed our subtraction, right? This is all still probably semi-confusing, but that's okay, and partially due to me occasionally just jumbling up my words. But here we're going to go ahead and clean up and return to our original function. So here we go, and we can add to the stack. Again, that's moving us up in memory 4 bytes. So that's removing C. We can pop ECX, which again moves ESP and removes that space on there. We can pop EDX, removing B. And then we can leave, which pops EBP, and we return to the address that ESP is pointing at, which would now be that return address that we had pushed onto the stack. Once that's done, all that memory that we'd used before for 5 and 10, we don't have to worry about it, right? Like it's long gone to where we left from. So let's go ahead and look at some assembly now. And it's going to be the same binary, so we already have kind of an idea of what we're looking for. And let's talk about what we see it doing, and do we think we could crack it again? So here we're looking in IDA free. I wanted to do this with essentially free stuff. I use Binary Ninja a lot. I like Radar. It looks really cool in the command line, which is a dumb reason to use it, but it's good enough for me. So at a high level, one thing that I'd like to talk about here is we have main and we have start, and those are not necessarily the same thing. But start is where in the beginning of our binary in the headers, it's telling us code begins. But here we actually have the the main function kind of called out for us. So we just go right there. It's a CTF binary. Who cares? And we can see here too that one thing I'd like to reiterate is there's not like a whole lot of different assembly instructions. So we see a bunch of pushes, we see some moves, we see subtract, we see an XOR, LEA is load executable address, and we see calls. And looks like we see a test and a return and a jump not zero. So that's probably like 10 different assembly instructions. And that's like everything here. So knowing what we see in here, we can see, okay, well, it's pushing enter password a string from data and then calling something that will actually post that onto the screen for us or post it to the terminal, whatever. And then we see that a crack me is there. And then we see a string comparison. And depending on how that string comparison goes, and if it's, the zero flag, if it's 0 or 1, we see that it goes a certain way. So we can see on one side we have correct, and we can see on another side we have wrong password. So knowing that we have a string comparison to crack me, we can basically say, hey, this is definitely crack me. And if we had entered that, then we would 100% be passing this CTF binary. So all of that's cool, but we still have some extra time. So I thought it would be fun to go through like a ROP chain, which is more of a applied version of reverse engineering. So I was trying to remember what I was talking about. It's been a long day. So reverse engineering is sometimes not its own end goal, right? Sometimes you have some kind of other output that you want from it. In this case, like an exploit. So we have here a ret to win binary that we're going to go take a look at. And this is from ropemporium.com, I believe. And a ret to win binary is typically one that you have to return from a function that doesn't actually have like a valid way to get to that function. So I think most compilers will kind of scream at you if you try to write like a function that's never used, and it'll be, highlighting everything in red telling you you're a moron and that it doesn't need to be there. And it might even throw up a compiler error when you try to compile it. But so we have a ret to win binary, like I said. This is actually an ELF binary, so it would look functionally in a hex editor a bit different from a PE file. But for what we're doing right now, we really don't need to worry that much. But let's say we went through and we just identified the function names and we saw that there's a main, there's a pwn me, and there's one called ret to win, which if we went to main, we would see like, hey, it calls pwn me. And then we want to return ret to win, obviously. So in the screenshots that you're going to see, by the way, I used object dump, which is just like if you have Windows subsystem for Linux, or if you have just like a bash terminal or whatever, like you probably have object dump. And you can type in like object dump -x and then whatever binary, and it'll spit out like a big amount of information, such as like your symbols. So stuff like, knowing something is called main or knowing something is called return to win. That's a symbol. You would see all that stuff. And then I'm also using GDB with pwn debugger installed. You'll see pwn tools and you'll just see Python 2. And before I get drawn and quartered for using Python 2, I'm being lazy because it prints natively to bytes. And if you don't kind of go out of your way to make something print to bytes in Python 3, then certain aspects of what I'm about to do would just be printed in Unicode and it wouldn't work. So I'm lazy about it. I don't necessarily recommend using Python 2, but hey, you're all trapped in this call with me, so let's go. And another thing to note is endianness, which I didn't really talk about earlier. So endianness refers to where the least significant bit is. So we're talking about the last bit, when we're talking about endianness. So I know the number 31 isn't binary, but we can tell that there's a significant number and an insignificant number, relatively speaking. So number 1 is inherently less valuable than 3 tens. So we would say that this is little endian, like the lowest number is trunked at the end. Whereas if for some reason we read things the other way around, potentially this number would be looking to us like 13, but it would still mean 31. It's just if you parse it the other way around, then you have to do it backwards. So we'll be looking at this, and it's little endian, so we'll have to if we have to mess around with memory specifically, then we'll have to basically go about things slightly backwards. But that's to explain up front why I'm doing it that way. So let's take a look at main. And what do we see here? A whole bunch of assembly nonsense that we may or may not understand. The important thing is going through here, we can see that there's several function calls. We can see that it sets a buffer. We can see whatever puts at PLT means. Frankly, I don't know. And then we see that we call the pwnme function, and we go over there. And then we see that after that we do something else, and then we return. And returning from, if this is the only function in there, returning means we exit it, right? So let's go and look at the pwnme function. So what do we see here again? Not necessarily a whole lot. We see that there's some functions. We see something is printed out at, printf at PLT. Then we see that something is read in at PLT. And then eventually we leave. So the main thing that I would try and take from this is that, again, we don't see the ret to win function here, right? We don't see any references to it. So we're going to have to sort of hijack command execution in order to get there. One thing to also note is, what do we see on here that we recognize too? We see push EBP, move EBP, ESP. We can see before each of these functions are called, we see variables being pushed onto the stack. We see push EAX. We see push 8048708. We see these different things specifically pushed onto there, where they may be pointers to strings, they may be whatever, but they are values that are called into there every single time before a function is called. We can see like executable address being put on there, whatever, and then we see at the end that there's like a leave, which would take us to our return address, and then we have return, right? So all of that stuff that we kind of recognize, and we might feel a little bit out of our depth, but like, again, we're looking at this at a high level. To see what a program is doing, we don't have to read every single thing. You can kind of skim the Cliff's notes and get what's going on here, right? So now let's look at the ret to win function. This, to us, appears to be an island function. We haven't seen anything that actually like goes there. So we do see that it pushes something onto the stack, and then it calls puts at PLT, whatever that does. And we see that there's a system call. We may not be sure what that does. And then we see there's a no operation. We see that it leaves and that it returns. And that's everything we know about this. So with what we know, let's go ahead and try to run it. So this is the screen for what GDB with Pwn debugger installed looks like. What I think makes this helpful is that you can see your register values up there. We can see EAX, and what was last on EAX was shell bin bash, where we were literally running this binary. So that was at some level part of a variable used in order to actually run this. We can see that EIP, the instruction pointer, which we didn't really talk about, is pointing to the next instruction. So we can see next that it's going to subtract ESP and add space onto there at memory location 804-8554. And if we continue through this, we'll see that the next thing it does is go to 804-8557. It's incrementing every single time by 4 bytes. So then we can see, well, it's not exactly by 4 bytes, actually. That's interesting, but neither here nor there. Then we can see that down near the bottom, we can see our stack. So we can see that ESP is on there. We can see EBP on the stack. We can see some just straight up values on the stack. But this is main, so we kind of know that we're going to go through here and that it's going to call us to go to pwnme. So here we can see that we're at pwnme. And we can see that our registers look a little bit different. We can see that our stack looks a little bit different. We're continuing to kind of go through and look at how things seem. And we don't see anything super interesting yet. But next, it's actually going to ask us for some kind of input. So what it says is, for my first trick, I'll attempt to fit 56 bytes of user input into 32 bytes of stack buffer. What could possibly go wrong? I guess a buffer overflow, but who cares, right? We're not, well, maybe you're a programmer. I'm not. So, not my program, not my problem. That's what I say. So we give it some input. And in this case, with pwn tools, I made a non-repeating pattern, and you'll see why I made that non-repeating pattern in just a minute. So we go ahead and we enter this objectively stupid input to just see what it does, which is partly what I like about reverse engineering, is that it can functionally be kind of the same as if your car's not working and you just start banging around with a hammer to see what happens. You'll start to see some really interesting program behavior, even if it's like an objectively kind of dumb approach to doing what you're doing. Like if you get into fuzzing or something, you might be looking at things in the headers and just being like, oh, what happens if I just tell the loader that this amount of space needed is, I don't know, 6 billion bytes or something? Like, does it just totally freak out? Does it crash? Does it just not work? Does it put memory out of bounds? Whatever. So here, we're going to see what happens when the memory flows out of bounds. So we put in that input and the program crashes. And if you look at our stack, kind of down there in the bottom, we can see na, then ma, na. I won't try to read out every single one of these, but we see the instruction pointer was overwritten. And that becomes very interesting to us because we know then that where the non-repeating pattern hit LAAA, which, each of those characters is a byte, we know that we can put a 16 or a 32-bit, address in there and maybe jump to whatever we want. And then this crashed though because LAAA, aka hex for 6161 whatever, is not a valid address to return to or to go to. There's no instruction there. So let's go ahead and then try and craft our exploit. And I'll see if that's audio choppy on my end. I'll try to put my face right in front of the screen. So let's go ahead and create our exploit. We did see that we overflowed, and we know kind of where we want to overflow from, right? Like we want to figure out where that LAAA is, and we could just, type it out again or spit it out with pwn tools and then just cut back to there. And so we could fix it that way, but we can also just say, hey, cyclic pattern, where did this pattern occur? And we know that it's 44 characters in. So we also see up here that the address we want to jump to is 0804862C. And if we recall from talking about Indianness, we're going to actually have to put that in backwards to feed it into the computer. So when we're creating our payload, this is just printing it out, but you would save this to a file and then run it as input for the process. We're saying, hey, Python 2, print me 44 A's in a row, and then print me this hex backwards. Print me 2C860408 because that's where we want to jump to. And then it'll spit out, this kind of failed character there, and then our A's that are screaming at the program to get it to do what we want. Which that's the function of A's, by the way. You need to intimidate your computers. So if things ever don't work, just like dangle your laptop over the side of a building and just scare it into working. So let's go ahead and run our payload and feed it directly into the binary. And here we can see, oh, this actually jumps there. And then it spits out our flag, placeholder 32-byte flag, and then it immediately segfaults. And why does it segfault? Because there's probably... the stack is utterly broken. We've overflowed into places where we should not have overflowed, so the program won't continue to work. But we did get what we wanted there, which was our exploit to actually run. And so then what becomes interesting is saying, like, hey, if I'm developing an exploit for this, how do I manage to make that work while saving my variables, saving my stack, returning to that so that it can actually continue working without things breaking? But yeah, so that's how that functions. And so before I take questions and everything, I do want to give some kind of greets and thanks and shout outs. So some folks that I think are pretty good on Twitter to follow. Malware Unicorn and Ophir Harpaz were some of the people who first had tutorials that I saw for getting into reverse engineering at a level more than, I guess, like playing around in hex editors and like aimlessly looking around in like IDA or whatever. So I would highly recommend you go and look at their materials because they'll explain things in their own ways. And Malware Unicorn in particular has just like a ton of content for getting good at this stuff. So NetSpooky and Binary Golf I want to mention in there because I think this is where I started to feel like this kind of thing had really interesting implications. seeing these things where like people would take binaries and say like, hey, if I cut out like all of the headers, does this run? And then being like, okay, it doesn't. Well, what if I cut out, all of just part of the header? Or like what if I find these things that are just like artifacts that were compiled to help the linker link but aren't actually needed to run the binary? Does it still run? Stuff like that. So major shout out to them for making that kind of thing really, really interesting. There's also my good buddy Birch Boy who is always putting out just really interesting content, I think. Rich in Seattle and Ryan Elfmaster put out some really, really fascinating stuff. You'll see a lot of those guys on Temp Out, just writing really fascinating work on mostly Linux research. So some websites I think are helpful. Obviously, over here on the right, so begin.re, really helpful for me. Openanalysis.net, I haven't seen like a ton of their content, but I know they have like a Patreon where they go through a bunch of tutorials and stuff and constantly streaming and helping people to get into this kind of thing. And they seem fantastic. Temp Out, of course, already mentioned. One thing that I would say is a great place to get samples is VX Underground. I would keep in mind all of the samples are password protected, so you would want to DM them on Twitter in order to get access, and they can tell you what the password is. But there's kind of a meme that's always saying it's infected, but I would just message them and don't worry about it because it's just people trying to bamboozle you. And then books, these were some that I thought were super helpful. POC or GTFO has a very important spot in my heart. It's so cool. So if you're going to read any of those, just read POC or GTFO and it will get you really excited about this stuff. You'll see like the coolest and dumbest projects you'll ever see. Like I feel like that's where you'll see something like someone writing an exploit for an emulator that inserts shellcode that allows a two-player or a second player an AI or something that wasn't even built in as a function. I don't know. You'll just see like the craziest projects there. And then also the header that I use that's like a IDA logo and ASCII from a really good homie that is always taking commissions, and I was really happy to commission them to make that little bit space, and I would definitely go check them out. They do amazing stuff. And yeah, I think that's it. So if people have questions or whatever, happy to stick around, and thank you guys for sitting through this.
Hey, that was awesome, cmex. Thank you so much for coming out tonight and talking about reconcepts. Super, super fun. Um, I guess we can open up the floor for questions. I mean, people can like drop a question in the chat if you want. We could all just like unmute ourselves and talk over each other like animals. I don't know. I don't know if there's any rules here. Any any questions? Oh, and yeah, actually, I'll continue recording. Maybe just to get a couple of questions in there, and if there's nothing, then I'll stop.
Yeah, definitely. I'll go ahead and just respond to the first one I see in there, and I'll read it out too for the sake of our viewers back at home. How long does it take to gain basic proficiency to have some fun with malware samples and or be semi-useful to boost a SOC blue team as a side gig? Straight up, like, play around this weekend. Like, look at like a royal ransomware sample or something. This might be like horrible advice, so listen to me at your own risk. But go and look at like a sample of ransomware or something and see like, hey, do I see like the ransom note in the read-only data? See like, oh, do I see things being called out that are telling me that there's a function in here that is encrypting? What do I see as um like imported functions from the DLL? What do I see as exported functions if it's like if it is itself a DLL? That kind of thing. So I would say straight up, like just learning that you can go and peek at strings in malware is like super helpful. Like I work in IR, and like a nice day for me is if I look at a sample and all I really needed to do is just find some strings. Like, is that easy for the threat actor to change? Sure. But like, have I also seen Royal Ransomware literally using the same ransom note for like 6 months? Yes. So like if you wrote a Yara rule for that ransom note, like it straight up it would function. Like it would be fine. It might not be ironclad, but it would be fine. And then the other thing I would say is like when I was hired into my role, it wasn't necessarily just as like, oh, you're like a master of reverse engineering. I think I'd been really focusing on it for like a year in my free time. And it was useful enough that every time they had malware, they threw it at me to look at because I was happy to do it. And yeah, the zoo is great too. There's so many different places to get samples. Like Malware Bazaar is pretty good. You can find a lot of stuff there. There's always like if you have like a fortune and you can get a freaking virus total account, that's always so sick. But yeah, there's so many different ways to do it. But yeah, just anything where you can find like forward movement and be like, how do I learn more about this? If you can have that attitude and not get too frustrated or just be willing to return to it every once in a while, like you will absolutely get good at it because I'm like utterly convinced that people don't get into this because they're arbitrarily told that it's more difficult than it is. Like how people are turned off from programming. Um, how do you not get rocked while playing with fire? That's another. So definitely do your reversing in a VM if you can. Now that I have a bit more experience, I would say that not everything I do is like insanely kosher. Like if I want to on a Mac or Linux machine download a .exe ransomware sample and pull it apart, I'm not really going to worry that it's going to pwn me. That's not to say that you couldn't get bamboozled and it might, but if you're just working in like a virtual machine and you disable networking capabilities and even if you enable like drag and drop or something like that, like I feel like you tend to be pretty safe. But I will also say if you really want to be hardened and do this like a non-reckless way that isn't just like some stranger on the internet being like, yeah, download some ransomware and run it, bro. Then there's definitely some good tutorials for going and like hardening your machine. I think if you kind of avoid just being on like a standard Windows machine and like downloading malicious .exes and like running them, that's like a good start. Any other questions from anybody? And also, if people ever want to just hit me up like one-on-one or whatever, I'm pretty approachable. I like talking about this stuff. I'm not like a giant turd all the time or anything. Oh, and while people think of things too, I know we're here for Prelude, and like I will interrupt what I'm about to say by saying like I do not work for Prelude. Like I'm not like a Prelude employee who's just like shilling something, but their solution is actually pretty sick from my understanding in terms of like the most annoying thing about getting a bunch of intelligence is being like, okay, well I have to figure out a way to make this actionable, right? Like just getting like an IOC or like a TTP or something in itself, if you just like collect it like numbers in an address book or something, it's not going to do that much for you. But if you do what they do and you make things immediately like freaking testable, that's actually like really dope within the context of blue teaming and making sure that you can cover what you need to do.
We might have like one more question in the chat. I'm not sure. I see somebody typing, but I don't know if there's a question. Oh, there is a question. So, do you frequently run into very obfuscated malware and hit a wall, or is it usually doable?
Oh gosh, that's a good question. So yes, that can be super frustrating. I'm not gonna lie, and a lot of that is where yeah, to some degree of doable. That's a good caveat. So so that is where having like a community of people that you talk to, I think can be very helpful. If something is like a straight up thing you're working on at work, you might not necessarily be able to just be like, hey, I'm working on this emotet sample and it's, customized for us and I want to know this. But like hopefully you have people you can kind of talk to. And then certain things like obfuscated malware, stuff like that, a lot of that is where dynamic analysis kind of becomes helpful. Like I've been working on unpacking something for a little bit, and the way I could tell it was unpacked and that it was where I needed to have it be was, I could see in the debugger as I was running it and kind of stepping through one little bit at a time that memory was being reserved. And then I could see data being copied into that memory. And then as we kept going through and deobfuscating, I could see a second MZ header appear. And that was when I was like, oh, here's the payload. And so a lot of it is really just being comfortable. I hate to say it, but being comfortable with failure. Like sometimes I'll go into work and straight up fail at what I'm trying to do for like weeks. But if you are just able to like feel okay with not knowing immediately and feel okay with like I don't know, seeking help and asking questions and taking a step back and being like, well, what do I concretely know? And how can I try to get more answers from that? And like, what else can I observe that I might be missing? You know, what can I take a look at? I think that becomes a really good exercise. And also, anytime you're stuck, you're probably going to learn a lot, even if you don't unpack it or, you know, deobfuscate it or whatever. And once you learn it, it's another thing in the freaking toolkit.
I have a question for you, actually. And
Yeah.
then, I mean, we're already like over time, and I want to be respectful of your time, so maybe we should end shortly after. But my question is, um, what do you recommend for like new reverse engineers that have, maybe read some of the books you suggested, they've done a course, they feel like they have like a good grasp on the basics or something, but they want to like actually go out and start doing stuff. So like when I did that, when I first started, or one of several times I first started, because I had a few false starts, I would like hit a wall and then like give up, because I didn't have like community support. I didn't have someone to go and like ask for help, and I might bang my head on like a wall for like 2 weeks or something and just get blocked. So like, do you when this happens to you or for somebody else that's just getting started, like what do you recommend? You go to Discord somewhere, go to Reddit, like reverse engineering Stack Overflow, like who should people kind of reach out to for a little bit of guidance or help when they inevitably hit those like first walls that everyone hits?
Yeah, there's a great reverse engineering Discord. I can try and link it, but I think it might be like a Reddit Discord or something like that. I'm not entirely certain, but it's a pretty good reverse engineering Discord, and I'm happy to link that in just a minute.
Cool.
And then I think a lot of it. So I kind of have to approach that question in a weird way, I guess, from my experiences where like I didn't really know other people doing this stuff. And so I would just occasionally like talk to people on Twitter about it or whatever. And I never had taken like a class, which that's something I still really want to, like a formal foundation. So a lot of it can be kind of brute force. And I think of it as like each time it's almost like a miniature CTF problem where you kind of have to indulge yourself and be like, hey, it's okay to failure because proper failure is just a part of iterative improvement, So like I think part of it is like part of it is mentally like, you want to make sure that you don't let yourself get super discouraged because if you get super discouraged, you're going to get tunnel vision on what you're looking at. And then part of it is having an attitude of keeping it fun, I think for me, like especially if you're trying to upskill specifically, then why not have it be something that you're kind of looking forward to? So going ahead and looking at samples for things that you're actually interested in, or if you're really interested in seeing how I mentioned emulators earlier, like I think emulators are kind of fascinating. So like going and trying to reverse engineer like a Game Boy ROM or something like that, going and poking at it and seeing like, hey, how does this work? Then from a more practical standpoint, I think having like a hard copy of practical malware analysis on your desk doesn't hurt. I'd say the Linux binary analysis book that Ryan Elfmaster wrote is freaking amazing. I learned so much from that. So if you can get a copy of that, it's amazing. Practical binary analysis I have. I don't feel like if you have the other two, you necessarily need it, but I wouldn't say that it's a bad resource. I definitely pull that out frequently. But really, the biggest thing I think is having kind of the CTF-ish mindset of here is what I know. It's okay that I don't know a lot, but how can I ask better questions and figure out what's going on? Because really, sometimes the best way for growth is just being willing to struggle and being willing to be like, oh, I feel like I hate this binary. I want to tear my head out every time I look at it. and just being like, you know what, it's okay to go and look at a write-up of it, or it's okay to wait until there is a write-up of it and to go and do something that keeps it fresh and fun. And that's not to say that you don't wind up sharpening your skills a little bit, but sometimes it's also like if you don't have that senior engineer or something who can give you the forward movement that you need, and if you don't have, you know, access to, you know, the SANS courses or the PhD guy who can just answer whatever, um, it's totally okay to basically be like, okay, well, in a sort of hackery way, how do I just make sure that I get forward movement from this at all costs? And think of it like there's no cheating in reverse engineering. That's how I'll put it. Like whatever you do to get forward movement and whatever you do to keep it fresh and fun so you keep doing it. Like if you just peek binaries every day, even if you walk away from some tough ones, you're going to get better.
So that's really great advice. And that makes sense. And thank you so much for coming out tonight. We're 10 minutes over. I have a feeling that we could answer questions all night long, but I think maybe that wouldn't be fair to everyone. So cmex, thank you so much. Congratulations on being our first community speaker talking about reverse engineering. I hope that you will come back sometime. Maybe we can all do this again. And if I get reverse engineering questions from anyone, I'm going to send them your way. So just fair warning.
Yeah, that's fine, and I'll pass them up if I can't answer them. But thank you so much for having me, and sincerely appreciate everyone even just listening to me prattle on about reverse engineering. And I hope it's a little bit more accessible and at least like a little bit more fun.
Awesome. Thank you so much.